This is VLSI data conversion circuits, lecture 51. In the last class we were looking at digital to analog converters, and one of the simplest methods of converting a digital code into an analog quantity is to perhaps use a resistor string, right, and depending on what the digital code is, you select the appropriate tap of the resistor string as the analog output. As we saw yesterday, there are several problems with this this basic idea. One, of course, is that the decoding logic is very complex. Okay. A further problem is that the output impedance of this DAC keeps varying with the digital code, which means that the output voltage developed when connected to some load impedance will be a nonlinear function of the digital code, because even though the settled value is probably okay, the way it settles to the final value is a function of the digital code, which means that if you are interested in dynamic performance, which is often a very important thing in a lot of applications, for example communication or things where the entire waveform is of concern, not just the settled value, then using such a DAC becomes a problem. On the other hand, there exist many applications where only the settled value is of concern, right, and a classic example is a flash A to D converter, right. You can think of the resistor string as basically being a D2A converter of a special kind where multiple outputs are available at the same time, right, if you want to, for example, right. The next, another way of converting a digital code into an analog output is to not add voltages, but add currents. So, to add voltages, what were we doing? We were taking this reference voltage, dividing it up into a whole bunch of small voltages which are represented by the voltage drops across these individual resistors in the resistor string, and to generate the final output we were adding up several voltages. Whatever can be done in voltage can also be done with current. Okay. So, for example, if one had a variable current source in some fashion, for example, say let us say this current depended on the digital code, and if you eventually were interested in a voltage, this current I, which is a function of code, will result in an output voltage which is R times I, which is a function of the code, where the op amp is simply acting as an ideal current to voltage converter. Now, several ways of realizing this current exist, right. You could have a whole bunch of current sources which were controlled by a digital code, right. We all know how to make many copies of the same current, right. We use current mirrors and then generate multiple copies of a same master current, and we also know how to turn a current source off. Okay. So, depending on the digital code, we can turn the requisite number of current sources on. Okay. Or exploiting the fact that this is a virtual ground node, one could have, for instance, make this Vref, and you have a whole number of identical resistors R, okay, and depending on the digital code you can either leave R floating or you can ground it, right. If the resistance is connected to ground, a current V ref by R will flow through the resistor, okay, and will result in an output voltage R f times N times V ref by R. This is the digital code. That is the decimal representation of the digital code, right. This is just a dual of the resistor string, where there to add voltages we had many elements in series, to add currents you have many elements in parallel. Okay. Now, one can think of several ways of implementing this current digitally, all right. So, one straightforward way would be to say, okay, this is my so called virtual ground to the op amp. For the time being, let us assume that all this infrastructure is there. So, as far as we are concerned, we are pretty much only interested in the current that is being pulled out of the virtual ground node, right, which will flow through the feedback resistor and gets converted into a voltage at the output of the op. Now, one can conceive of many ways of converting the digital code, and I mean one can rather, what I intend to say was that you can conceive of many ways in which the digital code can modify whatever resistive network we have to generate a current which is N times V ref by R. As a case in point, since we are talking about currents, we will always be getting quantities of the form V ref by R and so on, right. So, instead of keeping 1 by R, I will just denote 1 by R with the conductance G, all right. So, for example, let me take a 4-bit example. One conceivable way of converting this code into currents is to have one resistor which is 8G, one resistor which is 4G, one which is 2G, and one conductance which is G. The switch on the left is controlled by B3, B2, B1 and B0. So, the current I DAC is simply V ref times G times 8B3 plus 4B2 plus 2B1 plus B0, all right. While this seems quite trivial, one observation that I would like to bring to your attention is the fact that the logic required to control the switches is actually trivial, right. There is nothing, the 4 lines that come in are the same lines that go and control the switches. So, the decoding logic, so to speak, does not exist. Right. On the other hand, it is also possible to realize this network using 15 conductances, all having all right. So, when all the switches are turned off, no current flows. When all the switches are turned on, 15 G times Vref flows, and depending on the number of currents, I mean the number of currents, the amount of current you want, you can turn on as many digital switches as you want, correct. So, there are, in other words, there are 15 conductances, all right, and you need some kind of logic which I will simply call decoding logic. All right, which goes and takes the 4-bit control word that you get, or the digital input word, and generates an appropriate 15-bit signal, all right. The key point is that the number of ones in the 15-bit signal must be equivalent to the decimal value of the code that you put in, all right, all right. So, what kind of, can you name one code which satisfies that? One way of doing it is a thermometer code. So, this is often, this is the binary code as we all know, and one common thing to do is to make this a thermometer code. Understand? Of course, there is no earthly reason to say this must be Vref and these must be ground. An alternative thing is to you move all voltages by minus Vref, in which case the virtual ground becomes real ground, I am sorry, the non-inverting terminal becomes 0 volts and all these become negative, the direction of the current, I mean, remains the same. On the other hand, if these terminals were connected to Vref, a positive voltage reference, and the current that will flow in will be in the opposite direction, but all these are fundamentally the same. Okay. So, there are two extremes. Okay. Here we have a case where the decoding logic is trivial, and here we have a case where the decoding logic is pretty complex. So, to take n bits and generate 2 to the n minus 1 control lines, the logic must be pretty complicated, right, at least when compared to the previous case. And you can imagine what will happen when you want to have a DAC which is 10 bits or 12 bits, you need to have a 12 to 2 to the 12 is 4096 of these conductances, and more importantly 4096 control lines going to these 4096 resistors or elements, right. Okay. So, the question is, I mean, is this plain stupid way of doing it? or is there something that the latter solution offers which is not there in the former. You understand? There are, I mean, one can also conceive of something between these two extremes, right. Let us say you have the MSBs, right, are controlled using this thermometer type decoding. The LSBs could be controlled by binary decoding. Is this clear? Right. For example, instead of having B2 and B3 control 8G and 4G, I could take B3 and B2 and generate 3 control signals which go and control 3 conductances of 4G each. But these, what I have shown here, represent the extremes as far as decoding complexity is concerned. One is very simple to decode and the other one is very complex to decode, especially as the resolutions become larger and larger. I hope you see this. Okay. So, one motivation to go from this solution to this solution is to say, hey, well, this decoding is complex, but at least I do not have 2G there, right. 2G is a very bad word these days. You understand? Okay. Is there something else that you may want to? Usually in engineering we have noticed that if you give up something, you usually gain somewhere else, right, hopefully. The question is, what do we gain? Right, any comments?
Sigma delta already the
Oh well, okay, one okay, so he's made a valid point, but so his point is that if we were doing a delta sigma modulator, right, we know that our flash gives out thermometer code anyway. So in that case it would make sense to use the latter DAC, and that is indeed true in a delta sigma modulator, right. I mean, DACs like this, which are called resistive DACs, are used all the time, right. So it takes in a thermometer code and everything is fine. But let us kind of step back a little bit and wonder if there is more to this than just its utility as in a delta sigma loop where a thermometer code is inherently available. Okay. So if this was exactly twice G, and if this was exactly 4 times G, and if this was exactly 8 times G, and all these nominally identical elements were indeed exactly identical, then there is no difference between the two output currents, except that the decoding complexity of one is much larger than the decoding complexity of the other. In other words, in the absence of device mismatch, the obvious thing to do would be to choose the simpler solution, which is the so called binary decoded DAC, or simply the binary DAC. Is this clear? Now, what point he makes is a very valid and relevant one. We all know that none of these elements will all be within quotes exactly identical or exactly the right multiple of G that we want. Okay. They will deviate from each other due to manufacturing tolerances. And by the way, how do you expect to get 8G? If you want to get 8 times the conductance, what do you think you will do? Take 8 conductances of G and put them in parallel. So, I I mean you can't even argue that this is likely to be smaller than this because the number of conductances is appears smaller, right. That is not the case either if that struck any one of you. The 8G would, you want to get an exact 8 times multiple of G, the sure shot way of doing this is to take G and copy and paste 8 times. So, you can see that the total number of conductances used is 15, right, in both cases. So, the only real difference in implementation is area of the decoder, right. Now, if G is an error, in other words with mismatch, all right. What is happening? Every conductance is not really G, but some delta G. This delta G happens to be a random quantity, all right, characterized by a 0 mean and some standard deviation sigma, we assume it is Gaussian, and some sigma G. Okay. Now, let us try and understand the performance of the binary decoded DAC with mismatch. So, if an element G has an error which is normal and 0 mean and has a standard deviation of sigma G, can you comment on the error in the 2G element? It is also a random variable, it should be 0 mean. What can you say about its standard deviation? Pardon? Be root 2 times sigma G. Does it make sense? Right? You are getting 2G by taking two identical G's and putting them in parallel, right. So, the error will be, the variance will be the sum of 2 delta G's, and because they are random and uncorrelated, the variance will be square root of 2 sigma G, right. Similarly, 4G plus delta G4, and the delta G4 will be a random variable with 0 mean, and I will just make this root 4 sigma G, and okay. So, now let us look at the step size. I mean clearly if the individual currents change, right, it means that the DAC characteristic will be also moved from its ideal value. I mean the step size will now differ from the ideal G times Vref that we had earlier. Whenever the code changed by 1, if the elements were all exact and were what we wanted them to be, a change in the digital code by 1 should cause a change in the current by G times Vref. Now, because each of these elements is changed in some random fashion, it also follows that the step size will change, correct. So, let us see what happens when the code was 0 1 1 1. Okay. So, when the digital code is 0 followed by all ones, what happens? What is the output voltage, output current? If there was no mismatch, IDAC should be Vref times G, which is a common factor everywhere, times 7 plus
Okay, delta G plus delta G2 plus delta G4 whole divided by.
So, if the digital code is 7, the elements which will be excited are this, this and this, correct, and therefore, the errors that will creep in will be delta G plus delta G2 plus delta G4. So, this will be delta G plus delta G2 plus delta G4 divided by G. I am sorry, divided by G, correct. Does it make sense? And can you comment on whether these errors are correlated? They are not correlated, right, because they are all coming from different elements. Okay. So, therefore, the DAC current will be Vref times G times 7 plus a random quantity which is 0 mean, and can you comment on its variance? You do square root of its sigma G by G times square root of 1 plus 2 plus 4. Okay. Which is Vref times G times 7 plus square root of 7 times sigma G by G. Please note that the sigma G by G is a number which is dimensionless and is an indicator of how well matched the conductances or resistors are, right. So, this is a indicator of matching. All right. Okay. Now, when the code is 1,000,000, what happens to IDAC? Vref times G times 8 plus delta G8 by G. Okay. So, this is Vref times G times sorry, this must be a normal distribution which is 0 and square root of 7 sigma G by G. Okay. Now, this must therefore be 8 plus a random variable which is 0 mean and square root 8 sigma G by G. All right. Now, in other words, If there was no mismatch, if the code changed from 0 followed by all ones to 1 followed by all zeros, then the change in the current should be Vref times D, which is definitely true, correct. This transition is called the major code transition, this is just jargon, and is basically the flipping of the MSB for the first time as you keep ramping up the codes, right. Now, can we comment on the step size at the major code transition?
Vref into
I mean, this is a random variable, this is another random variable, right. You subtract the two random variables, okay. I mean, you can think of this as a Gaussian random variable with a mean of 8 and a sigma of square root of 8 times sigma g by g and so on. So, the step size will therefore be a random variable with g times Vref times 1 will be the mean plus 0 times square root of 15. And why is it square root of 15? Wait, yeah, we are subtracting two random variables, that is correct. However, what are we subtracting? We are subtracting delta g plus delta g2 plus delta g4 from delta g8, and all these are uncorrelated random variables, you understand, which is why the variances add in the square sense, and therefore, you get a square root of 15 times sigma g by g. Does it make sense? All right. So, this is telling you that the step size at the major code transition will have a variance which is not just dependent on the matching, but it is matching the variance of the individual element multiplied by the number of elements that are there, which is basically 2 to the roughly 2 to the n, okay, or the standard deviation is sigma g by g normalized to the LSB times square root of 2 power n minus 1, for a large n it is roughly 2 power n, okay, all right. So, why do you think this result makes sense? Okay, before we go there, let me ask you another question. What about the transition from 0, 0, 0, 0, 1, 1 to 0, 1, 0, 0? Can you look at this and tell me what the step size will be? It should be g times Vref times 1 plus n 0 root 7, very good, E by G, all right. And at this code transition, it will be by the same, it will be root 3 and so on. So, which is the worst?
0 followed by almost 2
So, the major code transition is the worst as far as the variance of the step size is concerned, right. Variance of the step size is nothing but what? DNL, right. So, the DNL is nothing but the ideal step size minus the actual step size minus the ideal step size normalized to the ideal step size. So, what is the sigma DNL you get here at the major code transition? Very good, it will be n 0 square root 15 times sigma g by g, right. In general, it is n 0 square root of 2 power n minus 1 times sigma g by g, all right. Okay. Now, let us put this result aside for a while and look at the INL. What is INL? What is the INL? By definition, it is the what is INL first?
deviation from the ideal.
Yeah, it is the integral of the DNL, that is true, but in this particular case much easier to find. We know the actual output, we know the ideal output, the difference should give you the INL. Of course, because the levels are statistically varying, it means that the INL is also varying statistically. So, what is the INL at the mid code? It is n of, at mid code what is the output? Let us say this is what we define as mid code when it is 8. So, clearly the ideal output should have been this. So, the difference is what corresponds to this part. Okay, when you normalize it to the LSB size, this will become n 0 square root of 2 to the n minus 1 8, which is 16 by 2 times sigma g by g. Right. This is clearly the worst case INL, because for all other codes this number will be, that number will be small. Okay. Right. I mean, please note that is only true when you go and fit the endpoints. I mean, this is after you remove the mean and offset. So, the first and the last points will be, by definition you pinned them. So, the maximum deviation will occur in the middle. Now, the question is, what happens to the DNL and INL when we use not a binary weighted DAC, but a thermometer decoded DAC. Please recall that this way of doing this, because it is based on a thermometer code, is called all right. So, now let us try and figure out what the ideal output voltage will be, the ideal current will be for a code N. It will be N times, or let me call this for code M. For a code M, the current will be M times G times Vref, but unfortunately every G has got some random error, and if M conductances are on, it means that there will be M random errors. So, let us call them delta G1 plus, so this must be M times Vref times G plus delta G1 blah 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 up to delta G M. Okay. So, IDAC for code N, code M. This is clearly a Gaussian random variable, M plus N 0 comma, very good, square root of M sigma G by this clear. Now, when the code is increased by 1, this becomes Vref times M plus 1 times G plus delta G1 blah 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 plus delta Gm plus delta G M plus 1, which is G times Vref times M plus 1 plus N 0 square root of M plus 1 times sigma G by G. Okay. However, what can you say about IDAC of M plus 1 minus IDAC of M? Is G times Vref, fine, times 1 plus N of see, that is the catch. It is tempting to conclude that this is 2m plus 1 square root to 2m plus 1, but that is not correct, because these random variables are not uncorrelated, right. Please note that this G1 through Gm is the same for both of them. The only difference between the two is this extra stuff that you have added, right. So, it is n of 0 comma sigma g by g, right. So, this means that the sigma of the DNL is A independent of the code, correct, and is given by n 0 comma sigma g by g, all right, and the sigma of the INL it is the same expression that we had. When these expressions are the same, thing that we had earlier, right. For a code 8 we had root 8 sigma g by g, right, in the binary decoding case. Here it will also be the worst case will become square root of 2 to the n minus 1 into sigma g by g, all right. So, the question is, of course, this all comes out of the math, but is there some intuition to this? We see that INL same in both cases, but DNL in the binary thermometer cases, it is binary case, it is square root of 2 to the n minus 1 times sigma g by g. In this case it is simply sigma g by g, all right. So, why do you think, I mean which is larger? And that basically means that the DNL you get when you use a binary decoded DAC will be a hell of a lot more at the major code transition than the DNL you get with a thermometer DAC. Is this clear? I mean that is what the math is telling us. Now, let us try and figure out why this makes sense. Why do you think this makes sense?
Same set of n resistors and one extra.
Yes, correct.
But in binary DAC you are using completely different sets of resistors.
Very good, right. So, the key point is to note that in a thermometer DAC, to change one step, right, what you are doing is you are adding one extra step where that step is the same regardless of the code nominally. So, you are only worrying about the variance of that particular step that you are adding, correct. Okay. On the other hand, in a binary DAC, when we make the major code transition, how are we getting this current of G times Vref? We are generating this small current which is the LSB of G times Vref by subtracting two large numbers, right. Earlier 7 different current sources were on, right, and what is happening when we do a major code transition is that the 7 current sources which are on were being turned off and a new 8 times LSB is coming on, right, and these errors are completely uncorrelated because they are happening in, they are coming from different unit elements, right. So, when you subtract two large numbers to generate a small number, I mean this is something that we all know, right. If we get a small number which is, if we get a number which is the subtraction of to large numbers, we know that that small quantity is prone to be very erroneous, right, because there is error here, there is error there, this large number does not know that this large, I mean what this other large number is doing. When you subtract, of course on the average you get the right value, but there will be huge variations. That is what this is telling, right. So, if the DNL is a spec, which it will often be, right. So, let us say you want a sigma DNL of say 0.25 LSB, this is just let me say 0.1 LSB. So, that 3 sigma DNL is 0.3 LSB, right. If this is what you want as a designer, it means that you must go and choose sigma g by g to be equal to 0.1 by square root of 2 to the n minus 1, which is roughly square root of 2 to the n, right, for a binary DAC, and should be equal to 0.1 for a thermometer decoded. Correct. What can you say about the INL? INL remains the same in both cases, all right. So, but what are we paying for in terms of a thermometer decoded DAC? Decoding logic. Is complex, whereas for a binary weighted DAC, binary decoded or binary weighted is also another common term, you get the logic is lot simpler. Okay. So, in the next class we will continue with more discussion on these ways, and you know that these are two extremes, all right. So, in practice when you have a high resolution DAC, the best path is probably the middle path, which is neither all binary nor all thermometer, right, something in the middle. Okay. So, we will continue after a break. Thanks.